Hello, everyone. This is Michael Dong, and here we're going to talk about episode number 4, reverse phase mobile phases, the fundamentals, and also selection. Here are some of the key points summarized in the slide. We can talk about all these topics to some degree. Retention factor K, partition coefficient big K, K, small k and big K is highly correlated under reverse phase condition. A separation by reverse phase is according to analyzed hydrophobicity or lipophilicity, also correlated with a term called log P, very common in use in the pharmaceutical industry. We talk about mobile phase solvent strength, and also there's generally two mobile phases being used, A and B, and the percentage of B is important. That defines the solvent strength. We would talk about selectivity alpha, mass spec compatibility, a buffer, and other mobile phase additive. And finally, an equation or a model called the linear solvent strength theory or model, where log K is inversely proportional to the percentage of the stronger solvent or mobile phase B. Other slides that define what is mobile phase. Mobile phase is a solvent to carry and move the solute or the analyze through the columns. In HPLC, the mobile phase controls the separations because it would determine the solute's retention factor, and also it controls the selectivity, differences of retention factors. What is mobile phase A and B? In short, MPA or MPB. In generally, one would use a binary mobile phase system in reverse phase. Mobile phase A, by convention, is the weaker mobile phase and is almost always an aqueous solution. Because water is a weak solvent in reverse phase, because it is a poor solvent for any hydrophobic component, which prefer or preferentially partition into the hydrophobic stationary phase under reverse phase condition. Mobile phase B is the strong mobile phase. It is generally an organic solvent, such as acetonitrile or methanol. A mobile phase in isocratic and in gradient analysis. Generally, the pumped can blend two mobile phases under either isocratic or gradient condition. In isocratic conditions, we use a fixed mobile phase composition. We can do it by premixing the mobile phase offline, or preferably using the pump to blend A and B by the pump. Under gradient condition, we gradually increase solvent strength, or the percentage of mobile phase B, the strong solvent, in order to push out more hydrophobic analytes from the hydrophobic stationary phase column. Gradient use higher separation power, often called peak capacity, for more complex mixture samples. Gradient separation are generally needed for purity assay to ensure that all impurities are eluded and can be quantified in the chromatogram. Here are the general requirements for HPLC solvents. First, a good solubility of the sample component. Second, it should not be corrosive to the HPLC system component, generally stainless steel 316. It should have high purity, generally low cost is preferred, and also high UV transparency would be good for use with the UV detection. Also nice to have low viscosity, give you higher column efficiency, and low toxicity, and also non-flammability. Here's a table on common HPLC solvent and their pertinent attributes. Okay, here's the list of solvent. A solvent strength called the Hildebrand index, which is defined under normal phase conditions. So for reverse phase, the opposite of the Hildebrand index, meaning that a large one number, such as water, is a weak solvent under reverse phase. Here's the boiling point. Viscosity, low viscosity is preferred because it would give you higher column efficiency because of low intrinsic diffusivity in these low viscosity solvent. UV cutoff or transparency is desirable, such as acetonitrile is very desirable because we would be able to use a more universal detection wavelength under these mobile phase condition. Here's also refractive index. So several common ones are tetrahydrofuran, acetonitrile, methanol water. Just give acetonitrile as an example. Here's the solvent strength. Here is the viscosity, which is very low, and the UV cutoff is 190. That means you can actually use 190 nanometer as the detection wavelength. Methanol would have a higher cutoff and have much higher viscosity. Here's water with a viscosity of 1 and also very good transparency. In this slide, we show the strong solvent in reverse phase called mobile phase B. This is by convention so that we would not get mixed up when we talk about A and B. Most common one are acetonitrile, methanol, and THF. So 3 bottles shown here with the structure. Methanol and acetonitrile are both very common, highly used. THF is discouraged. The use of THF is discouraged because even though it have great solubilization power, it is highly toxic. And also it's not safe because it forms peroxide. So once we open up a bottle of THF, which is without the preservatives, you have to throw it out after 6 months. THF is generally only used in GPC. I would say acetonitrile is the most preferred mobile phase B. Why? Because acetonitrile is an aprotic solvent. It's preferred due to its low viscosity, gives you higher column efficiency, and very high UV transparency. So it's a stronger solvent than methanol. It is also a proton acceptor, and because you have a triple bond in the acetonitrile solvent, is capable of some pi-pi interaction with the solute. Methanol is also very common, is a little bit less expensive. It does tend to give you higher selectivity because it can do more hydrogen bonding with the analyte molecule under what we call solvophobic interaction for reverse phase. It acts as both as a proton acceptor and a donor. Here is something interesting called the allotropic strength, described in Lloyd Snyder's textbook, and also in this particular reference over here. For reverse phase, methanol is weaker than acetonitrile and also weaker than THF. In one case study by Kevin Shook et al. Under this reference, here is kind of the equivalent strength, right? So if you use 44% of methanol, the rest is water. You only need 35% acetonitrile and 28% THF to give the same retention factor. Here we described more information on the weak solvent, which is mobile phase A. It is almost without exception always water and very likely to contain an acidic additive, particularly for pharmaceutical analysis. Most common acidic additives are formic acid, acetic acid, and very lightly trifluoroacetic acid, TFA, used at 0.05 to 0.1%. It gives you a pH generally from 2 to 4. The reason why we do a low pH is that it suppresses ionization of the residual cyanide groups on the bonded phases, and it uses better peak shapes for basic drugs. So this is a kind of an important attribute of using acidic additive. Occasionally, we will use a high pH mobile phase A for some column which is compatible under high pH. And in those cases, we would use something like 0.1% ammonia or around pH 10. A few more comments on the weak solvent, mobile phase A. Generally, a buffer are used, but they really should only be used for very critical methods, such as POD method for very complex pharmaceutical. I think that buffer generally is overused in pharmaceutical analysis. Everybody uses buffer, but in most cases, just acidified mobile phase are good enough if you pick the right column. Common buffers are phosphate buffer, a formate, and acetate buffer, also bicarbonate, typically at 5 to 25 millimolar. Buffer works best to stabilize pH at plus or minus 1.5 pH unit of the pKa of the weak acid of the buffer. So this is according to the Henderson-Hasselbalch equation. Okay, so if you are too far away from the pKa, then it would not be a buffer. It would not have any buffering capacity. It would be just a solution. Volatile additives are needed for LC mass spec application. You cannot use sodium chloride because it's not volatile and it would mess up your mass spec. So these HPLC methods are called mass spec compatible. One very common mass spec compatible buffer that I use quite often for HPLC methods is 20 millimolar ammonium formate at pH of 3.8, right at the pKa of formic acid. This table summarizes some common reverse phase, mobile phase A additive and buffer. You can see that starting with TFA, which is very common, DFA, phosphate, formate, acetate, carbonate, and ammonia. Those with an asterisk are mass spec compatible. Phosphate, which is, even though it's very common, it's also very good UV transparency, is not mass spec compatible. Here is the relative pKa. I want to give a plug to TFA, which is very commonly used in pharmaceutical analysis and in the separation of protein and peptide. It happened to be an ion pairing reagent, therefore give you a very good shape for proteins and peptide. However, because it's ion pairing, it also suppresses ionization for mass spec. So if one wants to do LC mass spec, the one that actually is preferred is called DFA, difluoroacetic acid, which give you both excellent peak shapes and also without too much of ionic suppression. So it's actually therefore even compatible with high resolution mass specs such as OB-trap or TOF, right? But we would never put TFA into an OB-trap or TOF. So DFA is a good additive for LC mass spec application for peptides. It gives you good peak shapes and also give you great sensitivity for both UV and in mass spec without too much ionic suppression. Here's the chromatographic process that has been described in earlier episodes, where we describe the entire chromatography process, showing you a mixture of A plus B with the faster eluting band A coming first, uh, going through a detector first, right? In the chromatogram, A is eluting first because it's less retained in the column. And then there's also less column band broadening for A, while B is definitely give you a broader peak. So the in column band broadening is a specific tied to the chromatographic process. In a microscopic view is very interesting too, right? So we have a single solid porous silica here, and we are using a station phase which is hydrophobic. So we are bonding a ligand such as C18 onto the surface of the porous silica, and one can see that A being more polar, a, the partition coefficient between the aqueous layer and also with the hydrophobic station phase is very much towards the mobile phase area, right? While B is much more retention, right? The arrows are bigger going down to the hydrophobic station phase. So peaks would get broader and also larger retention time. In this slide, we explain a little bit further on the fundamental chromatography. We are actually drawing a similarity between the retention under reverse phase condition with that of a partition coefficient. So reverse phase LC is a thermodynamic method, so we can describe the process of retention separation with the distribution between the mobile phase and the stationary phase. Now, in pharmaceutical industry, we typically define the hydrophobicity of a drug or the lipophilicity of a drug using something called a log P, right, where we partition the drug between K prime, between that of water and isooctane. We should talk about that a little later, how that relate to a K of retention factor. So the partition coefficient, K is equal to the solute X, the concentration not in the stationary phase, SP, versus that in the mobile phase, right? So if something is highly retained, meaning that something very hydrophobic, this concentration would be much larger, and this would be much smaller, right? So the K would be very big, right? And there are some correlations which can show you the similarity that can be derived in matching K with K prime, K with the big partition coefficient. So once again, to follow up with our discussion, the HPLC separation is dependent on both thermodynamic from the equilibrium constant on the partitioning, which is responsible for the retention, and the kinetic, where we have in-column, extra column broadening or peak width. These two factors are important and fundamental in chromatography. So retention of is dependent on the analyzed hydrophobicity, meaning that if you have a very lipophilic or very hydrophobic analyte, it would be retained under reverse phase condition. So hydrophobic analyte have higher retention or higher retention factor K. So we can actually measure hydrophobicity or lipophilicity of the analyte by measuring something called the log P, which when we partitioned the drug or the analyte between isooctane on top here and water below here. I'm sorry, the isooctane is in the bottom. So the log P or the log K or the equilibrium constant is equal to the solute concentration on the isooctane over that of water. So we can now if we can reduce the log K, if we can reduce K, by using, instead of water, you can use acetonitrile, because acetonitrile is much more less polar than water. You can see that the K, the log K or the K is much smaller, right? So when we use acetonitrile, there's much less partitioning into the stationary phase. Therefore, acetonitrile is a much stronger solvent, and we can use a gradient to push out a more hydrophobic analyte in a complex mixture. So we can say that the partitional equilibration constant, big K, correlate very well with the retention factor K of the analyte. Now here's a very important theory, or called the linear solvent strength model, as described by this entire book by Snyder and John Dolan, called High Performance Gradient Illusion, the Practical Application of Linear Solvent Strength Model, published in 2010. Now, here is kind of the explanation of how that works over here. So if we inject under reverse phase condition an analyte at 100% methanol, right? Because 100% methanol is a very strong solvent. We almost get no retention time, retention on the column. And when we lower the solvent strength to 70%, you can see the retention time increases quite a bit, actually exponentially after 60 or 50%, right? You can see how much it increases. So the best way to describe that relationship of retention versus the percentage of mobile phase B is by plotting the log of the K prime of the K. And in this case, invariably, one get a linear relationship. Okay, and this is the whole premise of the book, the linear solvent strength theory for reverse phase. So meaning that the log K of any analyte is inversely proportional to the percentage mobile phase B, and the relationship is almost linear. The different solvent type for mobile phase B also have huge effect on something called selectivity, and also on the which actually control the resolution. You can see that the three common reverse phase mobile phase B, methanol, acetonitrile, and THF, they do have different property. And the term selectivity actually is, even though selectivity is alpha, the selectivity term is actually alpha minus 1 over alpha. Okay, later on we explain in the resolution equation why that is so. So changing alpha by change to different mobile phase B or different percentage of mobile phase B is an effective way to separate a pair, something called critical pair, which is a closely eluting pair in our chromatogram. So mind you that if we increase the selectivity from 1.1 to 1.2, we can double the resolution. Here's some example, right? There's two closely eluting peak at 40% of natural water. The selectivity is 1.07, but if you switch over to methanol, because methanol is a weaker solvent, one do use less, right? So one do use more methanol, so you have to use 50% methanol to give you the same retention. And alpha here is 1.19, and the is much better than baseline resolve. THF is even stronger, and you only need about 30%, and the resolution actually happened to be even better. It's actually too good, right? Because typically one don't need a resolution better than 3, right? So if something is resolved too much, then you should use a shorter column. This is kind of a waste of resources if resolved by more than 3 or 4 or 5. Another case study of a mobile phase, which is comparing acetonitrile with methanol. We mentioned that acetonitrile is a stronger solvent, and also, but methanol has a different selectivity. So here is the structure of acetonitrile, and also with methanol. And we have two analytes here. One is nitrobenzene, and one is propylbenzene. uh, propylparabens. And we compare two chromatogram at exactly the same uh, mobile phase B concentration, except one is acetonitrile or methanol. You can see that because acetonitrile is stronger, the elution time is lower. Also, you can see the resolution is not as good because the selectivity is different. At 20% acetonitrile, much weaker mobile phase, the big K, the partition coefficient, is much higher. Therefore, you have much higher retention, and even worse for methanol. You can see the methanol retention is very, 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 very long retention time. So methanol use higher retention factors when compared with acetonitrile. It has very different selectivity. You can see selectivity alpha is quite different. Another case study, in this case study, is a case study on doing method development using an approach called the sequential Isocratic steps. I would explain what it is. Let's say we have a situation where we have to develop a method to separate 7 components. Okay, the 7 component is 7 substituted phenols, right? So we have a sample. We put in all 7 phenol in a mixture, and we inject them at 40% acetonitrile water condition. And in this case, we only get 5 peaks. So something's missing, right? So this is not a good method because it's not resolving all the peaks over here. So the HPLC condition shown here using a Sapelco Acentus C18 column, a mobile phase acetonitrile water as indicated by different concentration of acetonitrile, flow rate, the detection wavelength, and 7 substituted phenols. Now we continue to lower the solvent strength by going to 35% acetonitrile. Things are getting much better, right? You can see that the K is increased from 1.5 to 5, and it's almost there, right? The only problem is peak 1 and 2, or methoxyphenol and cyanophenol is not separated. But that is very easy to separate completely. We just drop it further to 30% acetonitrile. And then we have the beginning of a good method, right? So this is a good method, almost ready to be validated. You just have to do some fine tuning on the injection volume and other thing, right? So if your intention to to have an assay for the 7 phenols, this is the way to do it. You can do this pretty quickly within a few hours. Okay, in this slide, we demonstrate selectivity changes when we switch different organic solvents basically from methanol to acetonitrile using the same column, using the same grading condition. And we are using a more complex sample of 12 pharmaceutical. And these most pharmaceutical actually turn out to be basic, which is in blue. There are some which is acidic, which is in red. And there's some which are neutral, which is in black, right? And we're using this C18 column under these grading conditions. Yeah. And one can see that comparing methanol to acetonitrile, the elution profile of all 12 components actually has not changed, meaning that the elution order is the same, right? Except that it just moved forward because acetonitrile is stronger, right? So actually everything eluded at fastest time. And also you might be actually see that the peaks are sharper, right? So acetonitrile is preferred because of lower viscosity, give you generally sharper peak and more column efficiency, right? So that's why I personally prefer acetonitrile. It's also stronger and also more transparent, right? So here's one scenario where there are some changes, but the elution profile has not changed. The next example, much more complex. We're using a more different column. The station phase actually is more complex. A bonded phase, which is called PFP, standing for pentafluoral phenyl column, right? So it is column that's capable of a mixed mole retention, right? So on top of hydrophobic interaction, there's some hydrogen bonding, uh, polar interaction, so on and so forth, right? Now here we can see a substantial difference. You can see that the elution profile is no longer the same as C18, right? So you can see 1, 2, 3, 4. They are very different, right? Uh, and some peaks are actually not very sharp under these conditions. One can also see that there are tremendous changes of elution profile between acetonitrile and methanol because methanol is capable of hydrogen bonding, also a dipole interaction also, right? So by going through different mobile phase B, one can actually change selectivity and develop a method which is much more desirable, meaning that it can resolve all the peaks to baseline for regulated purity assays. So here is my summary. In summary, we discussed the fundamental and rationale on the selection of mobile phases in reverse phase chromatography. We mentioned that retention mechanism is primarily a hydrophobic interaction or solvophobic interaction where the solvent plays a role. Uh, the hydrophobic interaction actually is pretty weak interaction. It's called dispersive forces, right? So definitely not a strong one, which is good because then we have good mass balance. If you use something which is much stronger, such as a nonpolar, normal phase chromatography is not as reproducible. So the elution and retention of the analyte is dependent on the lipophilicity or the hydrophobicity of the analyte, or according to the log P. Also, dependent on the strength of the mobile phase, the type of the mobile phase, and the percentage of mobile phase, the percentage of mobile phase B in the mobile phase. The model called linear solvent strength model, meaning that log K is inversely proportional to percentage of mobile phase B, actually describe the fundamental of reverse phase chromatography very well. Mobile phase A is likely to be an acidified water, meaning water with some acid, such as TFA, formic, or acetic acid. Three of the most common acidic mobile phase. We very rarely use higher pH because a lot of time the compound are less stable in the high pH. Buffers are highly used, but they really should be reserved just for very critical method. If you have a simple method, definitely buffer is not recommended because it's much more painful and much more time consuming to prepare the buffers. Mass spec compatibility is really important. A method which is mass spec compatibility in HPLC is very useful for new drug development because then you can use mass spec anytime to ID an impurity. Acetonitrile is the preferred organic solvent for mobile phase B. Selectivity alpha, meaning differential difference of retention factor, a parameter used in HPLC method development quite a bit to separating peaks which are closely eluting, or called critical pair. Both acetonitrile and methanol have different alpha, different selectivity impact on HPLC retention. Here's my list of references. The textbook by Lloyd Snyder, Kirkland, and John Dolan. This other textbook, this is a little bit outdated by Dr. Horvath and Wayne Melander. This book, which is labeled red, this is more updated. And also the book on linear solvent strength model. One of the best white paper, concept paper on selection of mobile phases under reverse free condition is on this one, which is readily available and searchable and free for download in this LCGC paper in 2018 from myself and also Barry Boyer from AMT. And finally, those interested in high pH mobile phase. He is a very good references published in Journal of Chromatography in 2003. For more information, please consult these websites or subscribe to the channel for other similar episodes. Here's quiz number 4, mobile phase fundamental selection. And so these quizzes are really very good to test your retention of the subject matter. On that note, we'd like to thank you for your attendance and see you next time. I hope you enjoyed this video. Please subscribe for other HPLC topics and leave me comments or questions. Connect me on LinkedIn and also visit my website for other resources. See you next time.